Okay, this is part 4 of the tutorial video for ALTEVAL program describing the methodology for evaluation of alternatives known as Minkowski Distance. The methodology used for this particular algorithm is somewhat like TOPS's. It normalizes the values first of all, and then it measures the distance from each value to the ideal for each MOE. However, the difference between this and TOPS's is that TOPS's measured the distance from each value for each MOE to the ideal and also anti-ideal to the worst as well, and then got the ratio of the distance from the worst to the total distance, and the bigger of course the better. The bigger that number is the better, because you want to be far from the worst. But in Minkowski distance it only measures the distance from ideal, so you want to be close to ideal, so the lower the number the better. But instead it goes through one more operation after it measures the distance from ideal, and it keeps exaggerating this distance, and 17 times. It takes it to the power of 0.5, 0.1, 1.25 and so forth. 17 times it keeps exaggerating this distance, and at the end actually the output of this Minkowski distance operation is different than all others. All others, ranked the alternative, and scores also were reported descendingly. The higher, the better. In Minkowski distance, the output is how many times, let's say, alternative X became first. So as I said, because it exaggerates the distance 17 times, out of that 17 times, how many times alternative X became first, alternative Y became first, or so, and all of them. How many times each of them became second, third. So number of times that each alternative becomes first, second, and third is reported as the output, and based on those numbers it makes decision making easy for any user to go and pick up the ones who have got high ranked many times. So with that, let's just get started and see how it works. So the process is pretty much similar. You call for the input file and then just click on the Minkowski distance. You have the option to change the weight as well. I'll show that to you, and then we go through the mathematics of it using a simple spreadsheet example so you can understand better how the process works. Okay, as always we're gonna use that same spreadsheet that we applied for other methodology. It's the transportation planning example. Again, I repeat myself, the first column is alternatives, the categories or criteria, and then measurement of effectiveness or MOEs come to the second row, and you have to also type whether reduce or increase depending on the MOE and the objective desire, and then you put the values in, and now you've got your input file ready. Don't forget, usually it's easy to forget, you have to call this tab input, and now you're ready to basically process this data using ALTEVAL program. Alright, so this is, as you are familiar with, the page when you launch the ALTEVAL program. Control Enter in order to introduce the input file, which got created under C demo, and it's called traffic.xlsx, and enter. And just like what you have seen before, it's exactly the same. The categories are here, and each category has got one or more than MOEs, and that's it basically. Now the only thing is we want to click on Minkowski distance, and let's run it. quickly, isn't it? It gave the answer, it gives the output. Now this output is different than what we have got used to it with all other methodologies thus far. What it does, as I told you in the introduction of this video, Minkowski distance measures the distance from each value to the ideal. And because it got normalized already, ideal is the one which has got the biggest number, largest number. So it measures that distance, but then it goes through sensitivity analysis and it exaggerates that distance 17 times. Why 17 times? And how it exaggerates that distance? Because it takes that distance to the power of 1, 1.25, 1.5, 1.75, 2, 2.25. From 1 to 5 with increment of 0.25, that becomes 17 times. So it keeps exaggerating this distance to see the sensitivity of the process and how things change. As you know, this distance from ideal is exaggerated. And then the output simply tells you how many times each alternative became first winner, second winner, or third winner. And it gives you the total also. The total basically says, number of times that each alternative at least became, the first, second, or third. For example, in this one, in this traffic example, alternative 2, 15 times became first rank, first winner, and then that obviously 15, 2 times it never reached second rank or third rank, but 15 times, that's pretty good. 15 times it became first winner. And that last row is basically the relative number, that means the percentage over the total. So that's alternative 2 so far. That seems like a promising one to select as the preferred alternative. None of these alternatives made it first, second, or third. Alternative 17, based on some of those exaggeration and power that I described, one time it made it to second rank. And alternative 18, one time it became third winner. This is a good one. Alternative 24 seems like after alternative 2, 24 is a good one, because 16 times it became second and one time it became third. So which one would you prefer? Alternative 2, which 15 times became first, or alternative 24, which 16 times became second and one time became third? If you are just a little bit conservative, probably you go based on this, but then the difference is not much. Sometimes you come up with an alternative which many times it gets third rank, but very few times became first rank. So I still would go with alternative 2. And that's basically it. Alternative 29, 15 times became third rank, here it shows. And that's it basically. So based on number of occurrences that these alternatives made it as first, second, or third, or you could look at the total, at least became first, second, or third, you make your decision and you pick that alternative as the preferred one. And that's about it. Okay, now let's talk about the mathematics of Minkowski distance and see how the algorithm works. Again, I'm using that same simple and silly example. Really, it's too simple with limited number of criteria and limited number of alternatives, which you don't need ALTEVAL to analyze it. It's just like breaking a walnut with a sledgehammer using ALTEVAL for this simple example. But it's a good one to cross the message as how the mathematics works. And that's it. So the input data, as you can see, the different criteria has different unit of measurement. Some of them are in thousands, and some like the cost is in thousand, and these are in tens. the scale is different. This is rating, these are actual year, so they're inconsistent. They're apple and orange in a way, and we cannot do any mathematical operation. So the first thing, like any other process that I explained, any other methodologies that I explained, we need to normalize them. And in order to normalize them, we use a different formula for normalizing them in Minkowski distance. Simply we divide the input value by the max of this, dividing input value by the max. And if the objective direction is reduced, like cost, we subtract it by 1. This will put all the values within the range of between 0 to 1. So this table, the middle table, has normalized them between 0 to 1, and all of them, as they increase, they are better. So with that said, they are all consistent, and now we could sum it to get the best result. But the very first thing we do in Minkowski distance, we find the distance or difference between each value and the ideal. Each value and the ideal. For instance, here, ideal is Mary, because this is the highest number, highest score. Mary got highest score on this MOE. So we get the difference, and of course Mary gets 0 because 1 minus 1 is 0, and so for the others, right? So these are difference with the ideal. Of course you want to be close to ideal, therefore the smaller the number, the better here. And same time, when you calculate the distance, you multiply it by weight, so it's a weighted distance. And we have weight in this top table, and by default ALTEVAL first, it gives equal number of weight to both criteria. So because this has got 2 MOEs, then it gets 2, therefore this gets 2 also, cost gets 2, and then that means each MOE here gets 1, and then cost get 2, and then it has to be summed to 1. So therefore each of them get 0.25, and this one gets 0.5. So this gets multiplied by this last row, and now we have got weighted distance. Now I'm going to take this same table that shows here at the last to the next slide, which is this one. So we got weighted distance from the ideal. If we sum it up, these are the result, and the smaller the number, the better. So Mary, bingo, got the first winner, and it's a preferred option to be hired. And then the second one is Charlie. So this is the result. Now the process goes through sensitivity analysis. So these same numbers gets exaggerated by taking them to the power of 1.25 and then sum it up. Taking it to the power of 1.5 and then sum it up. It goes all the way to 1.75 to 2.25, all the way to 5 with increment of 0.25. So this is the summary result basically of all of them. So I've collected all the sums and put it in this table. So basically for each power that was used, these are the result, right? And then we rank them. So Jack consistently became 4th rank, Ali 3rd, Mary 1st, and second best is Charlie. In this particular example, because it was silly, you don't see variation, and all these candidates consistently stay at the 1st, 2nd, and 3rd and 4th, but many times actually you see differences when you have more alternatives, more criteria. And when it's to the power of 5, actually this is more, because it has exaggerated the numbers, and therefore it's more risk-prone related decision making here. And then the lower the alpha or the power is, it's more risk averse, because when the distance is exaggerated and still Mary insists to be number 1, so that means you'll be safe to really choose Mary. And then here of course it's same, but then there are cases that they're different. Then with lower power, if somebody hits it as number 1, that's mostly risk-averse decision making. Finally, the result is here. It's summarized. Jack 17 times became fourth, and then Ali 17, and Mary 17 times became first, and Charlie became 17. With that, basically, is the result for Minkowski distance. So this was part 4 of the tutorial video for ALTEVAL program. It covered the methodology known as Minkowski distance, and basically the input value is taken in the program, the values get normalized, and the distance from ideal is calculated. By distance we mean basically the difference, and ideal is the one who has got the best score in the normalization process. And once the difference between each and the ideal is known, it's also multiplied by weight. So we have got weighted distance. Then this weighted distance is taken to the power of 1, 1.25, 1.5, all the way to 5, 1 to 5, powers 1 to 5 with increments 0.25, and then because we are, and then the result is summarized, and because it's distance from ideal, the less the number the better, then we rank them, and at the end basically we show how many times each alternative got first rank, second rank, and third rank. Also the ALTEVAL summarizes that by saying how many times each alternative either became first or second or third. So that row of data is also shown as a result of ALTEVAL. With that, now we are ready to go to the next part, which is another exciting methodology known as K-nearest neighborhood machine learning, which has got some evaluation process, plus it does lots of other fun stuff.